No?
Yes, I've started the recording.
Okay.
Over to you.
Cool.
Yeah.
All right. So yeah, thanks everyone for joining the session. So I'm actually pretty excited about delivering this session because this is a topic I've been wanting to investigate for like several months now. And while I was putting together this content, I realized like educating others holds you accountable to educating yourself first. So yeah, with that said, today I'm going to be talking about how we can use our BTP service AI core to serve your own open weight models in production. So to start out, you might be wondering, like, why would we ever even need to deploy open weight models if we have pre-trained ones already that are available through the generative AI hub? So there are actually a few reasons. So the first reason is that you might want to fine-tune a model for a specific task. So for example, mapping ABAP code to business processes. So this is like an ongoing initiative I've actually been working on with NBCU for a while now. And once you like train or fine tune these models, you're going to have to deploy them somewhere. So this is where like the best practices around model serving come in, which I'm going to be talking about. Another reason for deploying open weight models is you might want to optimize inference cost. So if you're using an LLM for like a one-time experiment with large amounts of inputs and many inputs, you're going to pay a lot since pricing is usually token based for these APIs. And it might make more sense to deploy a model on AI Core and pay for the infrastructure, like the GPUs, just for the duration of the experiment, and then destroy the infrastructure once you're done. And then lastly, there are also tons of open weight models that are already fine-tuned for many different use cases that are available on Hugging Face, for example. And if you want to use those, you're going to have to deploy them somewhere. So AI Core is going to serve as that platform for deployment. And one other caveat is the reason I'm using open weight and not open source kind of stems from the fact that like and most of you guys are probably familiar with open source AI, but I think a lot of times this open source terminology is kind of abused. And you might have heard, for example, that like Meta advertises their Llama models as open source or Mistral models are open source. Even in the generative AI hub, we advertise that we have open source models. But in reality, for these models to truly be open source, um, they need to these vendors need to release the training details, like what types of training data was used to train these models, what are the training configurations, like the type of optimizer, the number of iterations of training, the architecture of training. So really, even though we're given the weights and the architecture of the models, which we called open weight, we can't really reproduce these weights most of the times. So that's kind of the difference between open source and open weight. With open source models, you can reproduce the entire model from scratch. You have all the data, you have all the training details. So yeah, there's actually this organization called the Open Source Initiative, which defines these standards for what is the difference between open source, open weight. And yeah, if you search that up, you can check it out. So now that I've gotten this open source, open weight dilemma out of the way, let me outline the agenda for the session. So I'll first start off by talking about the deep learning timeline and how the model techniques have evolved since the mid 1900s. Then I'll talk about this famous transformer neural network architecture, which is used in practically every single LLM, and even these computer vision models like Vision Transformer, CLIP, and so forth. Then I'll talk about why this transformer architecture poses challenges for inference efficiently. Fourth, I'll demystify some different inference optimization techniques like KV caching, optimized CUDA kernels, and some others. And then I'll move on to the different out-of-the-box options for serving transformer-based models in production. So this includes like your state-of-the-art inference servers like vLLM, Llama CPP, Nvidia Triton, and so forth. And then finally, I'll conclude with going over AI Core's functionalities and features, and I'll go through a demo of how we can actually serve open weight models on AI Core. So that'll be more application-based. All right, so to go back to the evolution of deep learning. So back in the 1940s, like in 1943 specifically, there were a few mathematicians and neuroscientists that actually modeled how our brain works using circuits. So they modeled a neuron using circuits. And when they modeled these neurons, they didn't come up with the training algorithm to learn the parameters of these neurons. They just kind of created a model without learning. So it really wasn't until 1957 when there was a psychologist named Rosenblatt who actually invented the perceptron, and he came up with a learning algorithm called the perceptron learning algorithm. And this was the first practical breakthrough in allowing like researchers and computer scientists to actually train neural networks using a formal algorithm. This like backpropagation hadn't been invented at that point. There was actually a dark age from when the perceptron was invented until like the 80s. During this time, like computers were advancing a lot, but it wasn't until the 80s, 86 in particular, when the famous backprop algorithm was invented. And backprop is really the core algorithm that's used in like every single neural network, including transformers, including diffusion models. This is the core to model training, really. So backprop triggered the second golden age where a bunch of new advancements came out, like the CNN architecture for image processing. And then again in the early 2000s, there was another dark age, not too much advancement. And then finally in like the mid 2010, early 2010 era, we had like a huge boost of different models coming out like ResNets, AlexNet, generative adversarial networks. And then finally in 2017, we had the transformer that came out, which was a major breakthrough. And that dives into, let me dive into this transformer a little bit more. So this was designed by Google researchers in this paper called Attention is All You Need. And this paper is actually supposed to be by Wikipedia, or according to Wikipedia, they claim that this is among the top 10 most cited papers of this century, being cited over 173,000 times. So it's a really, really popular architecture. And this is kind of the summary of the architecture. I'll go into it in a little bit more detail, but really it follows this, it builds off of sequence to sequence architectures. You have this encoder block and you have a decoder block. So after this architecture emerged, there were many models like BERT that came out that were encoder-based models. And then all the state-of-the-art transformers now are actually decoder-based transformer models. You also have like the T5 model introduced by Google, which was an encoder-decoder transformer, but those kind of models aren't used as much anymore. But yeah, with that said, let me talk about the transformer architecture a little bit. I think I found a pretty cool visualization actually, and I really like how this visualization works. So yeah, the transformer architecture. So this actually represents the decoder of the transformer architecture because most LLMs are going to be using this decoder architecture. So step number one, so suppose we have this input sentence which says data visualization empowers users to, and the goal of our language model here is we want to predict the next token given the context. Um, so the first thing we do is we create an embedding for this input sequence. So we have a tokenizer at the first step that's going to take these words and it's going to map these words into indices in a vocabulary. So your vocabulary could be like 55,000 tokens large, and the tokenizer is just going to take each word and map it to an integer. And these represent the indices in the vocabulary. So this vocabulary, for example, might have 55,000 tokens. So you'll see that, like for example, powers could be mapped to index 30,000. The next step is you have this embedding layer in the neural network that is going to map these IDs into these dense vectors. And these dense vectors are going to be 768 dimensions in the case of this particular architecture. And then what happens is, like these dense vectors, there is no positional information in these. So for example, if you scatter these words in a different order, like you switch around or you swap visualization and data, or you swap to and powers, these IDs are going to be the same and the vectors embeddings are also going to be the same. So that's where this positional encoding comes in. The positional encoding adds in some heuristic of where this token appears in your input sentence. So if your input sentence is 6 tokens long, you're going to have some kind of a mapping or some kind of information in this new embedding that is a concatenation of the original token embedding and the positional encoding that captures some positional information of where the token belongs. So that's what happens in the embedding layer. Then we have kind of the heart of the transformer, which is this whole attention calculation. And the reason I'm bringing this up is because attention is where there's a lot of optimization potential over here. So what happens with the attention is you take each of these tokens that are 768 dimensions long, and what you do is you create a feature matrix that is going to be 768 by 768, and you have 3 copies of this matrix. So these matrices are called the query, the key, and the value matrices, and each one of them are 768 by 768 dimensions. And these matrices are actually learned. So these are known as like parameters in a neural network. These are weights that are learned by the network during the training backpropagation process. So what happens in the attention calculation is we take the dot product of this positional encoded embedding with the query matrix, and you get this 768 dimension matrix. Then you take the dot product of the same token with the key matrix, and you get another 768 dimension matrix. And then finally, you dot the token or the positional encoding embedding with the weight, the value matrix. So now you have 3 times 768, which is 2,344 dimension long token embeddings, and we have 6 tokens, hence why the number of rows is 6. So that's how you create these key value query matrices. And now this is where the attention computation comes in. So with attention, what you're doing essentially is you're taking these dot products between the query and the key matrices. So you're going to take a dot product, like each token embedding is going to, like you're going to dot data with itself. You're going to dot data with visualization, data with data with powers, data with users, data with two. And the idea here is that these dot products compute this score that gives you some kind of a relationship. It kind of relates these tokens together. So this dot product carries some heuristic of token relationships and how words are related to each other. And then what you do is you scale these numbers between like -3 to 3 in this case. So you do some kind of scaling, and then you add what's known as an attention mask. And this mask just makes it so that words can't see words in front of them. So for example, if your query is the word powers, powers should only be able to interact with words that come before it, not words that come after it. Like powers shouldn't be interacting with users or two, and that's why these values are masked out over here. Similarly with M should only be able to interact with data, visualization, and itself, but not with words in front of it. Because this is going to create some biases if you allow words to interact with future words. So then you have these masked attention scores, and then you pretty much compute the softmax, which is another form of regularization to these attention scores. And this is known as your final kind of attention scores. And this computation becomes really, really expensive because whenever you're producing new tokens or new input sequences, you might be using the same types of tokens and you're going to be recomputing these attention values. So for example, if we have a new token we're trying to generate, like let's say we generate data, visualization empowers users to, and then we see the next token being generated as visualize. Then to generate the token after visualize, you have to pass in this entire input sequence again, and you have to recompute all these dot products. But a lot of these dot products will have the same value for tokens that we've already seen. So that's where we have these techniques like KV caching, which I'll talk about, but these allow you to essentially cache a lot of these attention values. So then what happens is you have these attention scores. So what you do at the end of the day is you multiply these token embeddings by the attention scores, and you get a new embedding for each token, which contains information about how this token relates to other tokens in your sequence. Um, and then you also have this concept of like heads in attention, and the idea of heads is like each attention head gets to see different parts or different spaces of your entire feature space. And that allows you to capture like different meanings of the word or capture words in different contexts. That's not that important, but if you've heard of attention heads, that's kind of the idea of it. And then you pretty much pass these token embeddings or these embeddings that contain the attention scores in them into these feed forward layers. It kind of has this bottleneck architecture where you're exploding the embedding space and then compressing it. And then finally, you are detokenizing by multiplying your output embeddings um, by a vector that is 768 by 50,000, where 50,000 is the number of tokens in your vocabulary. So now your output is pretty much 50,000 dimensions long. And if you apply like a softmax, you have a probability distribution over your output tokens. And then you can choose the token with the highest probability. So now if we generate the next token in this sequence, you can see this entire kind of computation process happening over here. And you see that visualizes the token with the highest probability. So that's kind of how attention works, in case you guys were curious about the architecture. But let me go back to the slides now. Um, okay. Yep. So, all right. So now, hopefully, that you guys better understand this architecture, let's look at this bubble chart that shows how the sizes of models have evolved over time. So this model that I just showed you, I don't know how many, I think this is like a GPT-2 nano model, which is maybe like in the hundreds of thousands of parameters. So really, really small model. But nowadays you have these insanely massive models. So actually, like after the transformer came out, you had models like BERT T5 and GP2, which had like hundreds of millions of parameters, which is much bigger than like GP2 Nano, which is hundreds of thousands of parameters. But then after these models came out, you have like Meta's Llama models, which became in the tens of billions of parameters. And then now you have like Mistral's mixture of experts models. You have DeepSeek V3, and these are not in like the tens of billions, they're in the hundreds of billions. So really, really massive models. And it's actually rumored that like GPT-4, for example, has like over a trillion parameters in its model. So as we can see, these models are getting larger and larger over time. And it makes sense because what researchers have seen with deep learning is that even over-parameterized models don't suffer from overfitting, like, for example, in traditional machine learning, where you have this bias variance trade-off, where if your model becomes too complex, you become overfit and it doesn't generalize well. With deep learning, it's really interesting because your optimization techniques like stochastic gradient descent and atom optimizer, these have these implicit regularization in them, which helps kind of with overfitting. So even if you're training with high model complexities or for many epochs, you still don't suffer from overfitting the same way you do with traditional models. So anyways, these massive models pose a lot of inference and serving challenges, which I'm going to talk about. So let's talk about how, like, if we wanted to, we could serve an LLM from scratch. We could build a really, really simple server using a framework like Flask in Python. Um, and we'll see that there are tons of inefficiencies here from an inference standpoint. So in this kind of naive inference server implementation, so the first step will involve a client sending a request to our inference server. So this request is going to be or actually, to start off, this client can be anything. It could be a user who's just interacting with the LLM through an API call, or it could be like a backend application or backend service that is using this LLM for inference or for some kind of logic in the application. So this request is going to be some kind of HTTP style post request, and you might have a payload like as follows with the prompt as your key and once upon a time as your value. That's step one. Step two is there's going to be some pre-processing that happens by the server. So this pre-processing could include steps like parsing this JSON, tokenizing the text using the tokenizer. So there's a lot of overhead here because first, Python is going to be this middleman between the client and the GPU. And Python has actually like a much slower compilation process compared to these lower level languages like C or C++ or CUDA, which is used for all the kind of GPU kind of control. And a lot of state-of-the-art inference servers are actually implemented with a lot lower level languages. So you see like Rust a lot of times, you see C, you see C++ and CUDA. And then also Python has this global interpreter lock, which kind of prevents true parallelization compared to other languages like Rust or even Go, for example. So this kind of makes it difficult to serve many requests at the same time and achieve parallelization. Now, in step three, what you're doing is you're moving your pre-processed tensors or vectors or tokenized embeddings from your CPU to your GPU memory. And the downside here is that with the naive implementation, this copying of tensors is going to happen sequentially for every single request. And there's something called a PCI Express bus, and this is like the cable that's going to connect your CPU to GPU. And this starts becoming the bottleneck for low latency. So many state-of-the-art inference servers usually do some kind of request batching so that you can minimize the number of data transfers from your CPU to GPU memory. So we'll talk about those optimizations as well. Step number 4 is also really inefficient, honestly. So in all inference servers and all kind of decoders, you have this token decoding that happens in an autoregressive fashion. So what that means is that in order to generate the next token, you have to wait for the previous token to be generated. So that's kind of an inefficient process just by its implementation. But if you do some kind of efficient manipulations, which a lot of modern inference servers have, and these include KV caching, like what I mentioned earlier, you have like flash attention and paged attention, which are optimized attention mechanisms. These also help kind of speeding up this autoregressive decoding. And then in the fifth step, you have post-processing. Not much you can do from an optimization standpoint here, but this is where your output tokens are detokenized back into a string. And then finally, in the sixth step, you have the server that's going to respond to the client. And with the naive implementation, again, these responses are going to be sent back synchronously. There's no batching of requests, and your GPU utilization is really low. Yeah. So there's a multitude of ways that we can optimize inference. And to be honest, like I'm not an expert in all of these or most of these, to be honest, but I can present them here at a high level. So we've already talked about some techniques like page detention, for example, and this kind of stems um, from many decades ago when paged memory was invented. But the idea of page detention is you can kind of store these attention matrices into smaller, more manageable blocks on your RAM, and they don't have to be like continuous memory locations. You can kind of distribute like all these attention scores can be stored in different memory locations across the computer, so you don't like it's just a lot more manageable. And then we also have like continuous batching, for example. And continuous batching is where you send your inputs to the GPU in batches rather than one at a time. And this helps increase your GPU throughput and lower your latency and help increase utilization, GPU utilization. Then you also have like techniques like quantization, for example, and every single inference server implements quantization. So if you see Ollama, for example, which I'm actually going to talk about later, Ollama allows you to run LLMs locally on your machine, and those are all quantized LLMs. And quantization just refers to this idea of compressing the model's weights or parameters to these lower bit representations. So usually models are trained with like 32-bit floating point parameters, but you can compress these parameters so they're like 4-bit or 8-bit representations. And you do have kind of like sometimes a accuracy degradation or performance drop, but the pro is that you can fit much more complex, larger models with more parameters into more memory constrained GPUs or even like edge devices which have only CPUs, for example. And then you also have like caching, and this really relates to KV caching, which is called key value caching. And this is where you cache a lot of those attention scores so you don't have to recompute them when you're generating new tokens using the same input sequence. So yeah, KV caching is implemented in really every single inference server. So yeah. All right. So ultimately, like I said, most of these inference servers inherit almost all of these different optimization techniques. This table is a little bit outdated. For example, vLLM does support quantization now, but the idea here is that every server does have their own trade-offs. Some of them have support for certain models, some of them don't have support for others. Like vLLM really shines because it has these optimized CUDA kernels for page detention, and it was one of the first to implement that. So really, if you wanted to, you could take that naive Flask server and you could implement all of these optimizations from scratch. But the problem here is you're kind of rebuilding the wheel and you're going to be building it a lot slower and a lot worse than how the wheel is built with these other inference servers who've been really specialized in this domain of AI model serving. All right, so let's dive into the practical part now of the session, which is actually using AI Core to do a lot of this heavy lifting for you. So in a nutshell, AI Core is really this managed Kubernetes platform, and this handles all of the scaling and load balancing for you. So for example, if your inference server is getting hundreds of requests at a time, you don't really have to handle the scaling. Kubernetes is automatically going to be this orchestrator that's going to be spinning up or bringing down instances due to the load appropriately. So there are three main features of AI Core. So the first feature that many of you guys probably know about and what most people use is the subcomponent of AI Core called the Generative AI Hub, where you have access to many different pre-trained models. The second component is that you have this infrastructure where you can train and serve models that are open weight, or you can train models even from scratch. So I'm not going to be talking about model training at all, but I'll show you guys how we can serve models on AI Core. And then finally, we also have model lifecycle and management. That's all kind of in one centralized place, which is AI Launchpad. And here you have access to like logging, prompt engineering, other types of experimentation, and this is all centralized in AI Launchpad. So as for our pre-trained models, which you guys have probably seen this slide a lot by now, but we have many different models, 35 plus available. And what's interesting is actually we have a lot of open weight models, and these are not being routed through API. These are actually deployed using vLLM, which I found out a few days ago. So there's like the AI Core Foundation team is actually deploying these open source models using vLLM. And we don't know how OpenAI, for example, or Vertex AI, Google is deploying their models, but chances are they're also using these optimized inference servers like the Triton inference backend or Hugging Face text generation or vLLM. They're using some kind of variant of these inference servers with these different optimization techniques that we touched on. So yeah, pretty interesting there. In terms of resource plans, there are many available. So these resource plans are pretty much just give you access to the infrastructure. So we have these basic CPU-only resource plans, and these are good for really light machine learning workloads. So think of like traditional machine learning, like your basic trees, your XGBoost, your SVMs, logistic regression, even really simple neural nets you could use these CPU-only resource plans for. Or if you're serving like really quantized models, you could also use the CPU resource plan. But then when you're training really large models, I'm not going to talk about training too much, but we do have this large resource plan for training with the V100 GPU, which has like much higher GPU VRAM. But yeah, and there's also some internal plans that I found out about where you can do like distributed training, and those plans have like 8 GPUs attached to them. So I can send you guys a link where you can read more about these if you're curious. But these plans are more of interest, and these are the inference specialized resource plans, and these are all GPU plans with the T4, which is kind of it's kind of a not as popular of a GPU anymore, I feel. But you can still use this for like models like YOLO or lighter weight neural nets, or embedding models, for example, that have less parameters. And yeah, these really differ in their GPU VRAM. So yeah, depending on how big your model is, you might need to use a bigger resource plan versus a smaller one. All right. So with that said, I'm gonna dive into the demo now. Uh, yeah, let me share my screen and show you guys demo. Okay. So you guys have probably seen this AI Launchpad interface a lot by now, I imagine, if you played around with the generative AI hub. So usually, like if we go to AI Launchpad, you select like these resource groups, and what you probably have seen a lot is this generative AI hub section, and this is where you can play around through this like ChatGPT like interface, and you can run prompt engineering experiments. But there's actually another section in the AI Launchpad, which is these ML operations. And this is really the area where you set up custom deployments for training or inference pipelines. So you can do a lot of this through the UI, but I've actually found that using the SDKs and APIs are a lot more stable. So I have a notebook that I'll walk through, and I won't go into like too much detail here. I know we're running out of time too, but the main idea is that so over here I've created two different inference servers. I've created one inference server that is using OLLAMA, and you usually have to create like Docker files. Because AI Core is managed Kubernetes, it expects you to have like these Docker containers running. So you're going to create these Docker files, which are going to have some structure to them. And like over here, the main command I'm running is this OLLAMA serve command, which spins up this inference server. Um, and I'll show you how to invoke it. So this is one inference server I've spinned up. And then you also have these serving templates, and these are like kind of like Kubernetes deployment templates, but AI Core kind of has their own serving templates, which they eventually map to a Kubernetes deployment template. But these serving templates allow you to specify different types of environment variables, different kinds of scaling configurations, your Docker secret, so that AI Core can pull from Docker Hub where your Docker image is stored. And then also like the resource plan is specified in this deployment template. Um, then I have another inference server. This one is really simple, actually. It's using another kind of backend called Ultra Analytics, which is similar to Olama, but it allows you to serve computer vision models. So I'm serving this YOLO computer vision model, which is for pose estimation, object detection, and this is served through Fast API instead of Flask, for example. Um, but yeah, let me show you kind of how we can now play around with these inference servers, and I think this is the fun part. Um, so because, yeah, so I'll show you actually first, we can actually see these deployments in AI Core. Um, so after I deployed them through the SDK in that Python notebook, if we go to ML operations and we go to deployments, you can actually see these deployments running over here. So we have this Olama deployment, and this is deployed right on AI Core. And then there's another deployment for the YOLO model. Also deployed on AI Core. So I've copied these URLs, and now if I open like a Postman or some kind of API client, in order to hit these endpoints, you need to get an access token from AI Core. So this is an access token that I've gotten. And now, for example, if we hit the Olama server um, and we pass in this access token into the authorization header, we can see all the models that are deployed. So I deployed two models. I deployed actually OpenAI has their GPT OSS 20 billion parameter model, and I deployed this on Olama, which was released just a few weeks ago, right before GPT-5. And we can even see their quantization levels. So this one is like 4-bit quantization. There's another model that I deployed called nomic text embedding model. And this is actually supposed to perform better than uh, the OpenAI's text embedding 3 small and 3 large. And I actually tested this with some SAP text, and I'll explain that in a second. But yeah, so we can hit these models. So for example, for the GPT model, I'll show you a text that I'll send to it. Um, so we can send a text like with the system prompt, you're an AI model inference optimization expert, and the user prompt is why is KV caching important? And it takes a few moments. This is still a pretty large model, and the T4 GPU is just not enough. So that even though I'm using the large AI core inference plan, it's still not enough compute for these kind of larger models. Uh, yeah, so this might take a few moments. But yeah, now we see this output over here where it talks about why KV caching matters and how it has less energy consumption, and there's fewer data movements, lower latency. So yeah, and then we have the text embedding model, which I also talked about. And this one, if we embed some kind of a text like open source is amazing, we can get this text embedding that looks as follows over here. And what's cool is if you use like text embedding 3 small and you embed the text J4D and you embed Joule for developers, what I found actually is that if you take those two embeddings and do a cosine similarity, you get a pretty low cosine similarity. And that's probably because these embedding models, like by OpenAI, haven't been domain adapted to SAP data. Versus if you take this model, first of all, it's been domain adapted to a lot of additional data. But on top of that, I noticed like the cosine similarity for J4D versus Joule for developers is like in the 60s, or there's like 0.6 range versus 0.4 or 0.5, which was the case with text embedding 3 small. So what's also cool with embedding models is you can fine tune them, like on SAP data, for example. So yeah, that's something we might investigate for product feedback tool too. Um, yeah, and then for the YOLO model, we can actually do inference similarly. So I have an image that has these have an image that has all these people, and we're using the YOLO model that takes in this image and produces these vectors that contain key points for all the different body parts in the image. So you have key points for your eyes, your nose, your ears, your elbow, and different parts. So this is the YOLO model in action on AI Core doing this pose estimation task. So yeah, that's kind of how demo works. And there's a ton of other tasks and open source, or sorry, open weight models that are available on Hugging Face. And you can deploy a lot of these on AI Core. So it's pretty cool. Even stuff for like OCR, document question answering, like if people are having issues with document grounding in Joule, or you're seeing that you're uploading the document and the PDF, like there are tables that aren't being converted to text, or you have more dynamic content with images. There are lots of other models to explore with that actually do the OCR a lot better. Yeah, so it's worth checking out. But yeah, with that said, I'm gonna conclude the presentation and I'll open up the floor to questions if you guys have any. Yeah, sorry, I know this might have been like kind of theoretical. I was just trying to like kind of balance both application and theory because I feel like in a lot of these sessions, like we have a lot of application, but there is some beauty in also understanding like what happens under the hood. At least that's what excites me a lot. So yeah.
Yeah, I could follow it greatly. Great presentation, Aman. I just have a question. How many open source foundation models have you tested on our AI core infrastructure so far? And where do you say is the limitation?
Mm, yeah, so I've tested a few. I've tested like YOLO. I've tested another pose estimation model called MoveNet. I've tested OpenAI's Whisper, which is text to speech transcription, or sorry, speech to text transcription.
Yeah.
Um, yeah, and then I've used a lot of the Ollama models. So the main limitation I found is that when you have models that are bigger than like 70 billion parameters, for example, you're really you're memory constrained. Like our resource plans are just not big enough for these larger models. And they do have some internal, like SAP does have some internal larger AI core resource plans. Um, and the problem with those is like a lot of times when you run a deployment, you'll see like your uh, inference or training job will just be hanging and you'll get a message saying waiting for resources or resources not available yet. And you'll be
Mm.
waiting for many hours and many days. And I think this is a common theme that we even see on like AWS or GCP when you're trying to request like larger GPUs, you usually have to like reserve them. So yeah, it's kind of hard to deploy these larger models. So I've only played around with models that are like under 50 billion parameters and quantized. Yeah.
Okay, yeah. Thanks. Yeah, I remember having also some issues when I was using the data attribute recommendation service for certain models. I mean, the what models were not particularly big, but I think at that time they had some issues with allocating the GPU resources for certain requests, and then the request just took for ages instead of being processed in a couple seconds, like they were usually processed.
Yeah, exactly. Yeah, right. Cool.
Yeah.
Any other questions or?
Yeah, I guess if we do not have any more questions, we can end the session. Thank you so much for the session, Aman. It was really, the presentation was really wonderful and it helped to show what was happening. Like you said, the behind what makes it interesting. So thank you so much for the
Yeah.
wonderful session.
Cool. Yeah. Thank you
Yeah.
guys all for joining, and appreciate the attendance and questions. Yeah. Have a
Yeah.
good rest of the day.
Yeah. Have a great day.
Bye-bye. See you.
Thanks,
Bye.
Aman. Bye-bye.
Bye.
Thanks. Bye.
Bye.